So for our agenda today, I'm going to cover what is NLP, how is NLP used out in the world. We're going to dig into text preprocessing, some of the ways that we clean our data in NLP, and we're going to try some out. We're also going to try out a little bit of parsing. We're going to cover a few of the more common language models. We're going to look at a bunch of different applications within NLP, and we're going to visit some of the challenges and considerations that arise as we do NLP work. And finally, we'll have a little bit of time for Q&A. Great. So what is NLP? We're going to start by conducting a quick poll. So hold on. Get over to here. So if everyone could go to pollev.com/MarielFrank843, you can fill in some ideas on what natural language processing is. And we're going to actually develop a word cloud using Bag of Words, which is a language model within NLP. And we're going to get a little bit of a sense, using Bag of Words, what topics are coming up the most. So feel free to turn and talk to the person sitting next to you. If you don't have someone sitting next to you, I highly recommend moving so that you have someone sitting next to you. And feel free to talk. It's okay.
Like I know what I'm thinking, but I don't know how to how computers are language.
It's read and interpret, I guess.
Human language.
Yeah, read and interpret human language. Yes. Oh.
You can't use
Then
word language to define something.
That's
Yeah.
Some kind of
speech text.
I'm going to give you another probably 10, 15 seconds. So try to get your responses in. Already seeing some themes pop up here. All right, great. So the biggest theme that we're seeing is text, which is very, very true to form. Text is usually what we are processing. We can also move from audio to text, but ultimately we're going to be processing text. We see using here, extracting human because the language that we're playing with is human language, data because the language is in essence broken down into a data format. We see machines, language, useful, analysis, unstructured. So that's an interesting one. Understand, and I'm seeing inferring, machines, algorithms. Great. Okay. So are any of these surprising to anyone? Is anyone totally surprised by this? Probably not. The thing is, what we're seeing here is a word-generated cloud using Bag of Words, which gives us a sense of topics. So using NLP, we're describing NLP. I'm going to get back into the slides here. I'm going to get back into full screen. So what is NLP? NLP is a domain at the intersection of linguistics, artificial intelligence, and computer science, with the goal of enabling machines to interpret, analyze, and generate natural human language. So you'll sometimes see natural language understanding, as well as natural language generation, both can fall within the confines of NLP. NLP really got its start in the 1950s, originally with Alan Turing, the famous mathematician. He developed this idea for what should be really an artificial intelligence. And he hypothesized that a computer would deserve to be called intelligent if it could deceive a human into believing that it was human. So this developed into the Turing test, which was used as a model for determining whether or not a program had artificial intelligence for quite some time. Almost around the same time, the 1950s, there was some machine translation work that began to develop, probably as a result of the Cold War. So that's really where NLP was getting its start. And originally, those two fields, trying to deceive humans into believing something was human, probably a chatbot, and machine translation, we're using different models, but eventually the two kind of came together into one field. So how is NLP used? And this is going to be another quick turn and talk. I just want to get a sense, what are some ways that you think you have used NLP today? So quickly chat with your buddy next to you. How have you been using NLP today?
They're two very different questions. I mean, yes.
Sorry, the question's like how we interact, not like us. So it's like.
Let's ask.
Yes.
Does Alexa count?
Yeah, absolutely. All right, so I'm going to pull up some examples of NLP. I want you to see, did any of these come up for you? Show of hands. All right, who has used spell check or autocorrect today? It could be on your phone. It could be in a text document you're creating. Who's used auto-generated video captions at some point today? Or seen them on YouTube? Who's used a virtual assistant, either in Alexa or Google Home today? Has anyone? No? Yeah? Has anyone used a search engine? What about autocomplete? Has anyone used spam detection? Did you look at your email today? If so, you were using spam detection. Did you go onto a news site and take a look at suggested articles? That also uses NLP. There's a lot of different applications within NLP, or for NLP, I should say. All right, so now we're going to dig into the meat of it a little bit. So before you do pretty much any task within NLP, you're going to have to clean your data. This is probably true of most data science. So how do we do that in NLP? This really breaks down into three parts. So the first thing that we do usually is noise removal. So noise removal is where you take everything out that you don't want. So this could be something like punctuation. This could be something like if you don't want numbers in there. This could be something like if you want to change all of your contractions into full, from something like can't to cannot. This is the stage where you just get things out of there. This is also where if you've parsed something, or not parsed, sorry, if you've scraped the web, you've gotten something from Beautiful Soup and it has a bunch of HTML in there, you're going to be using probably URL to get rid of all of that noise. There's going to be HTML all over the place, and you don't really want to deal with that. That's not necessarily helpful for you. The next step is usually tokenization, and tokenization has to do with breaking text into smaller chunks of text. So a token is either a word or some sort of phrase, and usually we we talk about words when we're talking about tokens. And this is useful because a lot of the time when we're trying to make sense of our text, we're going to be developing a language model which usually relies on breaking text up into manageable pieces. So usually tokenization is either word level or sentence level. Fortunately for us, NLTK. Has anyone ever used NLTK, by the way? Show of hands. Okay. A few of you have used NLTK. It's the Natural Language Toolkit. And it's a really common library within the domain of NLP, especially if you're using Python. NLTK has a great tokenization function. You can either break things up by word or by sentence. Next up, you have normalization. So normalization is this kind of bucket term that includes almost everything else that you could possibly do pre-processing-wise. This involves lowercasing and uppercasing. This involves removing stop words. Stop words. What are stop words? Stop words are any words that we don't really care about. So these could be words like the, of, in, on, that don't necessarily have much meaning. Now, do we have to remove stop words? Absolutely not. It's completely dependent on the context of what you're doing within NLP. If you are trying to generate text, you definitely don't want to remove stop words. This is actually probably going to be important for you. But depending on your context, you also might want to remove even more language. So you can increase your number of stop words if you're dealing with a particular topic and you know that certain words are going to come up all the time and you don't really care about those words and you're looking for other themes. Next up, we have stemming and lemmatization. So stemming and lemmatization are two ways of bringing words down to their root form. Stemming is a little bit faster. It's also a little bit more blunt. It's not necessarily going to look like real words coming out. But lemmatization, if it takes into account what part of speech the word is a little bit more finely tuned, and it's able to really bring words down to their root form. So for example, if you take the word was and it's stemmed, you're probably going to end up with wa. Why is that? Well, stemming kind of generally assumes that every word is a noun if it's not sure, so it just hacks off any endings that it can. And it's like, well, okay, there's probably more than one wa, so it's a plural, so let's just get rid of that s. Well, as if you have lemmatization, what you'd really like to see is was coming down to be. So before we move on, I want to make sure everyone has gotten a chance to pull up the repo that I had up at the beginning. Which is up. If you haven't gotten a chance, please do now. If you don't have things set up locally, you can use the binder link right here, and a Jupyter notebook will be opened up for you. And we are going to dig into some pre-processing. By show of hands, who here has used Jupyter Notebooks or something like it before? Okay, almost everyone. That's helpful. Cool. So if you have your notebook open, you can get into the pre-processing directory. And of course, we have a server error, because why wouldn't we? Okay, hang on one second. I, of course, relied on the binder link, and now I don't have it open locally. But in the meantime, here we go. Okay, so we're going into the preprocessing directory, and we're going to open up text preprocessing, the notebook. And we're going to walk through what's going on here. These are a few different ways that we can pre-process text. So the first thing we're going to be doing is importing the regex library for Python. So does everyone have this open? Show of hands, thumbs up. Okay, cool. So first, for those of you who don't know Jupyter Notebooks, Jupyter Notebooks allows you to run your code bit by bit with little stop points. So the first thing we're going to do is run this first cell. There's either a run button up here, or you can do, I believe, Shift-Enter on your computer, and that should work too. So run that, make sure you're able to import regex. And next up, we're going to import a few different functions within NLTK. Tokenizes word tokenize. So we're going to be tokenizing by word. We're going to import the Porter stemmer and the WordNet stemmer from NLTK's stem module. So let's run that, make sure that's working. Everyone good so far? Show of hands, thumbs up.
Can I ask a question?
Yeah,
Why
absolutely.
did you choose a particular stemmer?
So in this case, I'm just using the NLTK stemmer as an example. There are other libraries that have stemmers as well. Yeah. Does anyone else have any questions before we move on? Okay, cool. Next up, we want to make sure that NLTK is, we have a few different corpora that we want to import. This is punct, WordNet, and stopwords. So we're going to go ahead and download all of these. Yes.
Sorry, when is it possible to make it a little bit bigger?
Oh, yeah, that's a really good question. Let me see if I can do that. Hold on one sec. Is that better?
Much better, thank you.
All right. All right, hopefully no one hit a snag there.
What is
You should-
corpora, by the way?
Sorry?
What is corpora, by the way?
That's a really great question. So corpora are bodies of text. So in the case of something like stopwords, what you're importing is a full list of stopwords that exist. Okay. So next up, what I have here is a passage from Through the Looking Glass. I want you to turn and talk to your buddy, figure out another text that you want to preprocess. It could be an email, it could be something from the news, it could be from someone's Twitter feed, whatever. Just throw something in there, make sure that it's longer than a single sentence. You're welcome to talk.
Yeah.
And for anyone unclear, make sure that the text is going between the two triple quotes. This is Python's way of allowing you to do multi-line strings. I'm going to give you another 5 seconds.
Yeah.
All right, so we're going to run this cell. And all we did here was we assigned that string to a variable called text. And now we're going to dig into the actual pre-processing. So the first thing we're going to be doing is some noise removal. We're going to get rid of anything that isn't a word. Words, by the way, do include numbers. Digits are fine. But it will get rid of any punctuation in here. So if I do this, I should expect to see all of that sentence, or not sentence, sorry, all of that text without any punctuation, because I'm going to print it out. So here we go. You can run the same for your own text, if you haven't yet already. Yes.
Just understood. Do you want us to replace that text? Or
Yes.
Okay.
Yeah.
Gotcha.
Sorry, that wasn't clear.
So is
Yes.
there a reason you're replacing with a space instead of a nothing?
Sure. So the reason that we're doing a space is because in the case of some punctuation, it actually takes the place of a space. So we're just adding an extra space in. It shouldn't matter in terms of once we get into tokenization.
I'm thinking of things like apostrophes. Like
Sure. Yep.
It creates kind of a weird thing.
Yeah. Absolutely. All right, so next up we're going to be tokenizing. We're going to be using the word tokenize function from NLTK. So we're going to tokenize our cleaned text, and we're going to see, hopefully, a list of words here. And it should be all of the words that were included within the original text. So there we go. So you can run your own cell, make sure that that looks all in order. If you have any questions, make sure to ask.
It will just tokenize using space, right?
Sorry?
It will just tokenize using the space.
Yes. Yes. And next up, we're going to be stemming these words. So we're instantiating the porter stemmer from NLTK. We're going to create a list comprehension and save it to the variable stemmed, where we're going to stem each token that we've just created within the tokenized list. And then we're going to print these out because we want to see what these look like. So go ahead and do that for yours. And take a look with your buddy and chat about it. See what you see there. See if you see any surprises.
Stemming is supposed to be
I don't think it's gonna remove. Oh yeah, I actually think it's right. It's just remote line. Oh, not that. It's coming. It's coming. I don't know. I don't like it. Oh wait, no, never mind.
All right. Was anyone surprised by anything that they saw within their stemmed text? Go ahead.
What was this supposed to do? Just remove plurals?
So what What stemming does is it sort of lobs off prefixes and affixes. So it's just trying to bluntly bring words down to the root form.
Yeah.
It has no idea what part of speech it is. It has no knowledge of the language specifically. It's just trying to do its best. Yeah, go ahead.
Oh, one funny thing, I took an article about James O'Neill, police commissioner, who's just stepping down. When it stemmed it leaves the O in his name because it had an apostrophe after it. So you just have this one big O token in the middle.
Yeah.
All that text.
Nice. Go ahead.
It changed the word has to ha.
Yep.
I thought has was a plural.
Yep. Go ahead.
Two things. It did it from feed, so feed stayed feed even though it has the ET.
Mm-hmm.
And Google lost the E.
Yep. Go ahead.
Swapped Y's with, at the end of words with I's.
Oh, yeah.
Yeah.
Yeah, that's interesting, right?
Yeah.
Go ahead.
I got something even weirder. It changed the meaning of the word. Instead of ceiling, I have a sail
Mm.
without ing.
Mm-hmm.
Colorful color.
So it probably thought ceiling was a verb
Yeah.
and just lobbed off the ing. I know I saw some other hands. Go ahead.
That has changed important to import.
Mm. Yep. I think I saw some other hands up. I don't know other. Go ahead.
How we change during to dure, D-U-R-E.
Yep. Go ahead.
I have a question about the case before.
Yeah.
Important seems like an important word for
Yeah.
this, and it's turning it to import. It seems like a big deal there.
Yeah. Yeah. Depending on the purpose of what you're trying to do, stemming may not be the best choice. But it does do something. Go ahead.
Does it? Is there a way you can customize how it's stemmed?
That's a really good question. With NLTK, I'm not sure that you can. I think with other libraries that might be possible.
Okay.
Go ahead.
Is this just for English language? What if I have like Chinese document?
Yeah, that's a really good question. With NLTK, there are other languages that you can import. I don't know how much has been done so far with Chinese specifically.
So this one is just for English, or?
The body that we're working on right now is just for English. We can see whether it would work for Chinese. I encourage you to do so, but I haven't tested it out personally. Okay, go ahead.
Just briefly, what would be a scenario where this is actually helpful?
So this is helpful in certain scenarios where if all you're really trying to do is pull out specific word topics. Like if you're doing a bag of words scenario and you're just trying to pull out a few important topics, this will get you some of the way there. It might not be the most accurate way, but if you're trying to do something quickly and you want to see something.
All right, so not necessarily where full sentences are where you're trying
No.
to...
You definitely would not want to be doing anything where you care about full sentences here.
Right.
Yeah, that's a really good point.
So like category, if there's a thing where somebody has to name categories and you name it one way and I name it with a slightly different spelling, it might capture
Yes.
that we're trying to say the same thing.
Yeah.
Right. All right. Or British spelling versus English American spelling.
I hope so.
Possibly. Okay.
Yeah. All right. Any other questions before we move on? Right. So next up, we're going to try out some lemmatization. So we're going to try this out with the WordNet lemmatizer. And the lemmatizer, we're going to lemmatize every token. Again, we're going back to tokens. We're not going from the stemmed text. So we're going to be lemmatizing those original tokens, and we're going to be comparing this to the stemmed text. So you can go ahead and run this cell. And you should see something slightly different here. It might still not be great, which might be a little bit of a disappointment. And that's okay. And the reason that this might be a little bit of a disappointment is because at this point, we haven't passed in what the part of speech is for each token. So the lematizer doesn't really know which token is which part of speech. So if we want to make this a better lemmatization process, what we're going to have to do is pass in both the token and its corresponding part of speech. So because NLTK is oh so helpful, its part of speech tagger does not work for this purpose. So we had to build our own part of speech, get part of speech function. So I'm just going to show you what that looks like. And the way that we set this up, what we're basically doing is figuring out from the WordNet corpus, we're figuring out how often a given token is assigned as a synonym for all these various terms. So it could be, if you want to see whether something is more likely an adjective or a noun, you can check whether or not it's usually used, whether its synonyms are usually used as adjectives or nouns. So that's basically what we're setting up here. And we're really paying attention only, in this case, to nouns, verbs, adjectives, and adverbs, but there's a much, much larger list of parts of speech that we could be putting together. But in this case, this is really what we're going to pay attention to. So if we go back into text preprocessing and we run this, we're just going to be importing that function. And now we're going to try lemmatizing with the part of speech. So as you can see, this is pretty much the same as before, but instead of only passing in that token, we're also going to be passing in get part of speech called on that token. And we should see the text lemmatized with part of speech. So this should look quite a bit better. So let's take a look. And you're welcome to do a quick turn and talk and observe. What did this do well? What did this not do well?
Sorry, so what does lemmatization do?
Yes, so lemmatizing is a more finely tuned way of bringing words down to its root form.
But it converted seem to seem, right? So it's doing the reverse.
So yeah, in the case of seem, seem is the base form of seem.
Actually, no, that's
No, my question is on the cell number 8.
I think
On number 8,
Yeah.
so what is the original lemmatizer doing?
Yeah, because like from cell number 7,
It treats, at this point, it's treating every word as a noun. It's just defaulting to the idea that every word is a noun.
So it converted seem to seem. Why did it do that?
Are you talking about seemed?
Yeah.
So why in this case is it seem?
No, from 7 to 8.
So the original, if you look at the original tokens,
Okay.
it was seemed.
Okay.
In the case of the stemmed text,
Yeah.
it knew to lob off the ed, right?
That's
Okay. But in the case of the lemmatized text, it was treating this as though it were a noun. So it didn't know to lob off the ed.
Okay, I see.
Does that make sense? But once we passed in the part of speech and it recognized that this was a verb, it was like, oh, okay. Now we know this should have, ed is an ending for past tense, so we can take that off in order to get back to the root form.
So then what's the benefit of doing 8?
What's the benefit of doing 8? This was more for the purpose of just showing you, first of all, if you happen to have a text that's all just full of nouns, if all you're really paying attention to is a bunch of nouns, then this works fine as is. But if you are paying attention to a text that has more than just nouns, you are going to want to pass in the part of speech. Go ahead.
So in 2 instances of the phrase natural language processing, one processing remained processing and one processing became process.
Ooh, that's really interesting.
Yeah. And the one that remained processing was capitalized. I don't know if that interprets that as a noun.
That could
The
be.
other one was lowercase, so
Mhm.
I thought it was a verb. I'm not sure what's happening, but that's interesting.
Yeah, that's a really good question. And it would be really interesting maybe if you ran lowercasing beforehand
Yeah.
to see whether that makes a difference. So next up, we're going to do a quick test of stop words removal. So the first thing that we would do is import the stop words corpus. And we're going to specify that we're concerned with stop words in English. And we're going to print these out. We just want to take a look at what words we're dealing with here. So you can go ahead and run this. And we see a whole bunch of different words. These are really, really common words that, in the case of a lot of texts, wouldn't really matter that much in terms of the actual overall topic. So if we see something like into or through, not necessarily going to tell us very much if the topic is murder mysteries. If we are concerned with, a poem where we care about I, you, me, things like that, then we probably wouldn't want to be using this stop words list, and we can actually create our own. But this suffices for a lot of different contexts, so we can always use it. Go ahead.
Why are there so many negative? I will guess that I don't want to remove that from the meaning of a sentence.
Yeah, so it totally depends on what the context is. So this is really just going to be for a situation where you are more looking for overall topics.
Okay. And if you have this list of words, you can basically just make your own list of actual stop words.
Yeah, you can make a list of stop words from scratch, which is something that a lot of folks will do when they're doing their own, both for Bag of Words and for TF-IDF, which I don't know whether we're going to have time to cover TF-IDF, but it's a sort of inverted form of Bag of Words. All right. Does anyone else have any? Oh, go ahead.
Do you know why there's just single letters in the stop words?
Single letters, yeah.
T and MST.
Yeah. So a lot of those are from contractions.
Okay.
Yeah. That's a really good question. All right, and we're just going to run this last cell, and we're going to see what our original list of tokens looks like if we get rid of all of those stop words. So again, this is going back to the tokens. This is not going to the lemmatized form or the stemmed forms. So you can go ahead and run this cell. And we should have a little bit more of a sense of the actual topics now from the text that we just processed. Does anyone have any questions about text preprocessing before we move on? You good? All right, fantastic. I'm going to jump back into the presentation. So you've gotten a chance to use both regex and NLTK here, which is a really good start. You've actually done some NLP now, if you haven't before. Okay, so next up, we're getting into parsing. So parsing is all about picking out specific pieces of language that we want to pay attention to. So one of the things that we often do with parsing is part of speech tagging because we want to find specific phrases that have a particular grammatical pattern. So we might be interested in noun phrases, we might be interested in verb phrases, we might be interested in something where you have verb, adjective, or verb, adverb, and noun, or something like that. And and we can use part of speech tagging in order to specifically select those chunks from our text. But things can get a little tricky, right? As you can see here, I saw a cow under a tree with binoculars. English is ambiguous, and a person, a human, can really figure out that the most likely scenario in this case is that it's the person who has the binoculars. But the computer can't. So that's been a challenge within natural language processing, is being able to figure out how to break these chunks up in a meaningful way.
But isn't that a misplaced modifier? And so shouldn't you just kind of exclude that from your text because it's bad grammar?
Which is bad grammar?
That sentence is like a misplaced modifier. That's kind of like a no-no. Okay.
I would say that this is a fairly acceptable English sentence. It might not be the most clear sentence,
Right. Okay.
but it is an acceptable English sentence. And there is a lot of ambiguity. If you read headlines, sometimes somebody will write something in the most atrocious way because it makes sense to them, as a native English speaker, but when they have it out there, a bunch of people will read it in a completely different way. And that's a common thing that happens with just ambiguity in general. But the truth is, usually we as either native or just fluent speakers of a language are able to determine, okay, well, this is the most likely scenario. But as I said, unfortunately, computers are not there yet.
Yeah.
At least usually. Another piece here is named entity recognition, or NER. So NER is when we're trying to find usually proper nouns, or we're trying to find special topics within a sentence. So usually, if something is capitalized at the beginning, we're going to say, okay, most likely this is going to be a named entity of some kind. Another interesting topic within parsing is dependency grammar. So dependency grammar is where we break language up into language trees. NLTK and Spacey both are able to do this to some degree. Spacey's a little bit better at this. NLTK has a really nice display function for it, though, and that's something I'd actually really like to show you. So we're going to go back into our Jupyter notebooks, and we're going to go up a directory and into the parsing directory. And we're going to open up the dependency parsing notebook. All right, and I'm crossing my fingers this is going to work because I've had issues with this, with Spacey importing here. We'll see. It imports beautifully locally, of course, but we'll see how it does up here. So what we're going to do is we're just going to create a little dependency tree from a sentence that we add here. So first things first, we're importing Spacey, and we're loading an English corpus. And we're going to just call it, when we load it in, we're going to call it a dependency parser. So we can run this cell. And of course, I get errors. Okay, can't find model. I'm going to try this again. Might need to. Give me 1 second.
I had to run the stuff in the comments at the top.
Sorry?
I had to run the stuff in the comments.
The stuff at the top too.
Yeah. Sorry, no, just the Spacey download.
Sorry, the what?
Spacey download part.
The spacey download part.
Once I did that, it worked for me.
Are you talking about this line right here?
3 down.
3 down. This one?
Yeah.
Yep, I just ran that.
Okay.
Sometimes likes to throw errors. We're going to try this with loading the Conda environment and see whether this happens.
So they are saying that you cannot find the core WebM from Spacey library.
Mm-hmm.
Is it some kind of established library?
Yeah. This is more of a Jupyter Notebooks / Binder issue and less of a Spacey specific issue. But for some reason, NLTK never has issues with Binder, so go figure. Okay. Loading some stuff in. Apologies for the technical difficulties. In the meantime, while this is loading, if you're able to run it, please do. You can replace, where it says my sentence, you can replace this sentence with a new sentence. And make sure it's just a single sentence, not 50 lines of text. All right, I'm going to try a slightly different version of doing this kind of import. 1 second. But in the meantime, work to get your own sentence here. And you're welcome to turn and talk to your buddy to figure out a fun sentence that you think would maybe be confusing for the machine, or maybe you think it'll work out really nicely for the machine.
Oh, yeah.
I got this error.
That should was
Because it's only
I might have to restart the notebook. I had to do that for mine because the
Thank you. That makes sense. No.
Sorry, no. Just
Mariel,
Yes.
if you're able to get it working just once you do your install by restarting the kernel.
Restarting the kernel?
Yeah.
Okay.
I don't know if that.
Okay.
Well, mine says trust.
Let's try.
And then commenting out the install stuff again. If that.
Commenting out the install stuff?
Yeah, because that already went through once.
Yeah, that worked for me.
Awesome. Thank you. All right, cool. Seems to be working now. All right, hopefully everyone has a sentence in here now. Does anyone have an especially awesome sentence that they would like to share? And I'll type it in here so we can watch it live. Go ahead.
I like to eat apples and bananas.
All right. I like to eat apples and bananas. Throwing it in. All right, we're going to run that. And now we're going to use the dependency parser to parse out the sentence. And we're going to parse each word in the sentence. And we're going to learn a little bit more about what is going on with that word, what the part of speech is, whether there's any other information that Spacey wants to tell us about it. So we're just going to do that first, just to get a sense of what we have here. So we start out with I. It's a personal pronoun. Tags it as PRP. We have like, a verb, non-third person singular present. We have to, infinitival. We have eat as a verb. It's a base form. Apples, it recognizes that it's a plural noun and recognizes that it's a conjunction that's coordinating. Bananas is, again, a plural noun, and it recognizes the punctuation as a punctuation mark. So we have a period, and it's a sentence closer. Okay, so from here we can see a little bit of what Spacey knows about this sentence. So next up, what we're going to do is we're going to import the NLTK tree functionality, which is going to allow us to print out a dependency tree from what Spacey has to offer. So let's run this cell. And finally, we're going to print out this sentence as a little dependency tree. So we'll see what it gives us. So it's recognizing that the sentence revolves around like. Dependency trees, by the way, are not the same thing as all sentence trees or grammar trees. You're going to see for dependency trees, the focus is always on the verb. So I is connected to like, eat is also connected to like, and then it recognizes that the to part is connected to eat. It's not connected to I. It's not connected to like. Apples is connected to the eating. Again, not connected to the liking. And we have this conjunction here, and then we have bananas. So this is just a kind of fun activity. This isn't necessarily something that you would be doing as much with your NLP, but this gives you a sense of the underlying understanding that your program is able to develop about human language. So we're going to move back into the slides. And we're going to move on. Okay. So language models. You're going to be, if you're staying for the next tutorial session on NLP, you're going to be covering language models, I think, fairly more in depth than what we have here. So I just wanted to give you a basic overview of some of the language models that exist here. So bag of words is one of the most common. It, again, is what we used when we generated that word cloud at the very beginning for an understanding of what NLP is. And really what bag of words is doing is exactly what this GIF is explaining over here. It takes a bunch of words and spits out the word counts. And that's really all it's doing. It's a mapping of each word to the number of times it appears. And you can do this as a vector. You can do this just as a dictionary like this. depending on what your use case is. Bag of words is also called the unigram model because it is connected to n-grams. So what are n-grams? N-grams are sort of an extension of what's happening here. So if you want to know how many times, for example, and the appears, you would be able to figure that out using an n-gram model. That would be, by the way, a bigram model. You can keep extending, by the way. You can have n-grams going for an infinite number of words in a row, but at a certain point, you have less and less information. So it's helpful to kind of play around with n-grams and figure out, okay, are trigrams the right way to go? Are something slightly longer, something slightly shorter, and from there you can also make predictions about text. And this is where you can start getting into text generation, by the way. Because what you can do is you can say, so how often does and the appear before bananas? How often does and the appear before apples? And from there you can start to figure out a way of generating text. So some common libraries that you'll see for both of these models, these are, by the way, statistical language models. These aren't getting into any kind of neural networks or deep learning. So some common libraries are NLTK and scikit-learn. Who here has used scikit-learn before? Pretty much everyone. Not too surprising. Scikit-learn is great for data science in general, including NLP. So beyond this, there are a lot of other ways that you can go with language models, but in essence, language models kind of split down into either statistical models or neural language models. And there are two pretty common neural language models at this point. There are LSTM-based models. LSTM stands for long short-term memory models, which are a type of neural network that I'm not going to get into the mechanics of the whole thing, but if you Google LSTM, you'll get a sense of all of what is going on inside an LSTM cell. But they're actually very, very helpful models for making sense of language. There's also transformer models, which have been developed a little bit more recently, and the real advantage there is LSTM models really only move sequentially from beginning to end, so it can really only process language from the beginning of a text to the end of a text, whereas transformer models are able to process in any direction, which is kind of cool. So they have become more and more frequently used. If you've heard of BERT, if you've heard of Elmo, those are transformer models. Those are also specifically pre-trained transformer models that are getting a lot of attention these days. And funny I should say attention, because attention is one of the big focal points of transformer models. I'm not going to get into it right now. It's a whole deep rabbit hole. Anyway, you'll learn a lot more about language models in the next tutorial session. So some applications. So once we have our text pre-processed, maybe we've done some parsing, we've picked a language model, now we're ready to figure out what do we actually want to be doing. So some common applications of NLP are topic modeling, text similarity. Text similarity, by the way, can break down into not just something like spell check. You know, you can figure out whether or not a word is close enough to misspelling, but also something like plagiarism detection. So there's a broad range of topics even included within text similarity. You can also get into sentiment classification and analysis, so you can try to figure out whether reviews are positive or negative on Amazon. So Amazon definitely employs this, by the way. This is something that they care deeply about. You can also get into bias detection. I've seen some pretty interesting work done using parsing to determine bias detection. I'll include that. Actually, it's in the GitHub repo. There's a bit on detecting gender bias in Harry Potter using parsing. You can also get into predictive text. If you have a Gmail account, it has probably already converted to a point where it's predicting your sentences. This can be kind of concerning, this can be exciting, but it is a facet of NLP. You can also get into machine translation. There's a lot that's getting done there. Google Translate has made a lot of headway, but there's a lot more to be done. And we can get into topics of language accessibility. We can get into text-to-speech, speech-to-text, and any kind of video captioning, closed captioning, anything that auto-generates text based on either audio or maybe even sign language is helpful. Okay, so what I have here displayed is an example of what's called a word embedding, which is oftentimes really helpful with topic modeling and is also helpful with text similarity, largely because we can talk about text similarity beyond just the, whether or not a word specifically looks like another word or a piece of text looks like another text, but you can also get into, is there enough in common topically between two texts? So what's really cool about word embeddings here, like this is word2vec, is you can say something like, from a mathematical standpoint, king minus man is going to give you queen, which is pretty mind-boggling. But I highly recommend looking this up later. This is pretty neat stuff that gets done. All right, so moving on to some challenges and considerations. So with great language processing comes great responsibility. I'm sure you've heard this quote before. There is a lot to consider. Natural language processing has a lot of applications. It is everywhere in our everyday lives now. You remember when we were trying to come up with all of the ways that we've used natural language processing tools today already, and it's only 10 a.m. It gives you a sense of how ubiquitous it's become. So because of that, we really need to pay attention to what we're creating. It is very easy to create accidental biases through the model that we're building or through our training data. Who here remembers when there was that Twitter bot named Tay? Yeah. Is everyone? Okay. So do you want to explain what that was? What happened?
I remember she started over time learning what was being tweeted out there and sort of tweeting some pretty racist stuff, and it was like a big shitstorm from Microsoft, if I remember.
Yeah, absolutely. So what happened there was the Microsoft team thought, oh, let's create this model. We're going to release it into the world. It's an unsupervised model of machine learning, and we're going to put it up on Twitter. It'll learn how to interact with people and become, more human-like. And really, ultimately, what happened was the data that it started pulling in was really racist, really sexist, really, basically, it sounded like a giant troll. So Microsoft obviously didn't plan for this. But this is the kind of thing that happens when you don't have control over the training data. And even if you do have control over the training data, you have to be really conscientious about what data you are feeding this model. There's some really amazing work also. I highly recommend, if anyone has not read Kathy O'Neill's Weapons of Math Destruction, that gets pretty deep into why we really need to pay attention to both the model and the training data. We also have to make ourselves aware of privacy and transparency issues within NLP applications. As we have Alexa and Google Home listening to us, we have our phones listening to us. What does that mean for us? What does that mean for other citizens or other people of the world? So it's something that we need to pay attention to as we develop natural language processing tools. So another big facet, and this is more of a challenge, is language variation. So language variation exists. Not everyone speaks the same English. Not everyone speaks the same language even. And people might even speak varied versions of different languages. We speak different dialects. We speak different registers. Most tools that we're developing in natural language processing at this point are built for and by English speakers. So there's going to be a bias there in terms of what's available. And it's not necessarily going to generate tools that are going to be useful across different languages. I actually just spoke to someone at a conference a couple of weeks ago who was telling me about how in Latvia they had to recreate an entire system for developing chatbots because the English chatbot systems that exist don't really apply to Latvian. So there's a lot, I mean, first of all, there's a lot to be done there, but of course that also means it's really exciting because there's a lot to be done there. We can get deep into other languages, we can get deep into slang. If you're trying to determine whether something is positive or negative and you get slang involved, that becomes way more confusing for varied computer models. Anyway, there's a lot of challenges and considerations within NLP. I am actually going to leave it up to questions at this point. I finished just a little bit under time, which I'm really excited about. I was nervous about going over. Does anyone have any questions? Yes.
So a lot of machine learning and data science is focused around pre-processing, like 90-95% is how you do that. So I'm curious, we did the tokenization and we did the stemming and that stuff, but what about misspellings of words? Because that seems like a really hard thing to do.
So that sometimes is done at the noise removal step, and you can use varied other models that already exist in order to help you out with dealing with misspellings. One of the really common ways that used to be done was Levenshtein distance, if anyone's ever heard of it. Which can be really helpful. A lot of spell check models rely on that.
And follow-up to that would be, is the same process used when you're in a very domain-specific language?
Can you, sorry, maybe I should bring this over there.
I can talk louder. Is the same process used when you're looking at very domain-specific language? So like if you were reading through a scientific paper or you're looking at a document written by someone that's very technical. So those words aren't necessarily part of most common models, or spell checkers for that matter. With the same process, I guess maybe just Levenshtein distance then.
Yeah, I mean, Levenshtein distance is one way of tackling that. There are other models that exist at this point. There are, certain models like, I know, for example, Grammarly employs deep learning in order to tackle a lot of those issues. But it comes up short sometimes. For example, one of my colleagues at one point was talking about palindromes, and Grammarly suggested that they change the word to pun because palindrome is not a good word to be using, is what Grammarly suggested, because, Grammarly is being a deep learning model hadn't necessarily come across the word palindrome frequently enough. Yes?
Just throwing down deeper on the Levenshtein principle, if I understand it correctly, it's based on the number of characters that need to be changed for two strings to match.
Yes.
In practice, how do you arbitrarily give it a number? Let's say if the two strings are only off by like 5 or 4 characters.
Yeah, that's
Arbitrary, or?
So it's going to depend on what kind of model you want to be using, right? So you can tweak that as needed. NLTK actually has a Levenstein distance function, so you can employ that if you want to check it out. But for example, if you're trying to use Levenstein distance for spell check versus for plagiarism, you're going to be using different counts.
And another thing, can you talk a little about catastrophic getting problem?
The catastrophic, sorry?
Getting problem. So like if you train your own model,
Mm-hmm.
then I've had the issue of when I train my own model, it forgot what the default entities were.
Oh. I'm probably not the best person to speak to you about that. The folks, so this tutorial is going to be followed in this room by a language models tutorial, and then I think after that by a deep learning one. So I would say speak to potentially the language models folks, but otherwise to the deep learning folks about that. Any other questions? Go ahead.
One of the big topics this week in PyData has been, I guess, like ethical data science
Mm-hmm.
and ethical modeling. And I know there's a lot of applications of NLP in like in recruiting and that sort of thing.
Yeah.
Talk a little bit about like the efforts going on in terms of like trying to make it more ethical and being responsible with the models that we're building.
Sure. So this is something that seems to be going on a company by company basis, unfortunately. It would be great if there were, a regulatory body of some kind that said, hey, you need to pass such and such criteria in order to really make this work. But it's not, that doesn't exist yet, unfortunately. But I do know that, for example, Amazon pulled there was, I think, a resume scanner that was happening, and they had developed some sort of resume scanner using a machine learning model, and they were really, really excited about it. But of course, the data that they fed it was from past overall experiences that they had had with previous candidates. So they fed, a bunch of resumes, and they said, these are the people who ultimately got hired and stayed for X number of years, and these are the people who quit pretty quickly, or didn't even make it past the interview rounds. So the model wound up favoring, based on that training data, of course, white men, and specifically ones who played a particular sport and went to a particular college, and it just was not really what they had been hoping for, unfortunately. But yeah, that does factor into recruiting a lot. Any other questions? All set? All right. We're all set. Anyone is welcome to chat with me specifically later. I'm going to probably be milling around this room in this area all day. So thank you so much.